our final project for discrete structures, which is about temporal and category-based price similarity network analysis for on the CPA data of Pakistan. So our goal is to show how prices in different Pakistani cities move together over time. Now, the CPI Consumer Price Index is really important because it is used for inflation management, policy, and cost of living. Now, if two cities have really similar CPI movements or indexes, and any sudden change in one city is likely to show up in a connected city. So, which is why using cosine similarity network analysis is really helpful in such cases. So, we're going to work with 17 cities, 7 CPI categories, and data from 2023, 2024, and 2025. And each data item has its associated variables as well. Now each now our products are divided into 7 categories for ease of showing our results, including food, meat, oils, fruits, non-food items, utilities, including miscellaneous items. So first of all, we had to convert our data set from PDF into Excel forms. We did this using pandas libraries, as you can see, you'll see ahead. A- And we also had to handle missing data rows. When we faced missing prices or broken rows, we ended up dropping the rows that were fully empty and then kept them with real values. And finally, we had to normalize our data by subtracting the mean and dividing it by the standard deviation across the cities, so that all of the cities are in a comparative scale, because you cannot really compare the cities and extract the cosine values, and you have different draw prices. And we also added a city feature matrix in which each city has its whole year's worth of price data for a particular category. Now for the cosine similarity to vector, we calculated cosine similarity between two cities to judge the similarity of the price indexes. If the cosine similarity, as given in the formula, came close to 1, it means that the price patterns are very similar. But if it's closer to 0, then the price patterns are very different. We computed this for each pair of cities, for each year, and for each category. And finally, to convert each cosine similarity into a graph, we use a threshold. If a threshold, if a cosine similarity is greater in a threshold, then the graph included edge between the two cities.
Okay, here we are using Google Colab, mounting Google Drive and setting the folder path. Then we define the list of CPI cities, map each item into one of 7 categories, and choose our main parameters like similarity threshold, saw, and the category importance weight, like here. Then these functions load the PBS CPI tables from PDF or from a cache CSV, clean the item description, convert everything into a long format, and then compute the z-score normalized prices for each item, city and month year. Uh, then here we build the city price vectors for a given year and category using the normalized prices, and then we compute the cosine similarity matrix between all pairs of cities. Then these functions take the similarity matrix, apply the threshold tau, and build an unweighted price similarity network for every combination of year and category, with cities as nodes and edges where the similarity is high enough. Then calculate centrality measures. This function runs degree centrality, closeness centrality, betweenness centrality, and eigenvector centrality on each network, and stores the 4 centrality values for each city, year, and category. Then after this we have metric weighting scheme. Here we find different ways to weight the 4 centralities. One scheme gives equal weight to all. One uses correlation to reduce redundancy, and one uses entropy to give more weight to metrics that carry more information. Then here we calculate city influence scores. In this part we combine the 4 cities into a single influence score for each city, year, and category, and then we aggregate across categories using the alpha weights to get one overall score. Then these functions compare the edge stats across years, build the temporal relation P based on edge inclusion, check the partial order properties, and then build Hesse diagrams to show how the network evolves over the years for each category. Then here we fix for each city on a simple Pakistan style map and define helpers to draw network. Then these functions build weighted graphs for where edges weights are the cosine similarity values and then compute similarities across categories using the alpha category weights to get a single weighted network for each year. Then we have the function to plot similarity heat map. And finally, in this main cell, we call all the functions in order. We load and normalize the data, build all the network, compute centralities and influence scores, construct the temporal relation and Hesse diagram, and then generate all the visualizations for different tau values and weighting schemes.
After building our yearly networks, we used temporal relations to understand how price similarity changes over time. So a temporal relation basically checks whether the connections of one year are fully preserved in the next or not. Mathematically, it is given by this statement, which shows that if we have a set of edges of an year B and it is the subset of another set which consists of all the edges of an year A, we then say that A is in temporal relation with B. It is useful in analyzing whether the city price behaviors are strengthening, weakening, or staying stable over the years. We then use Hayes diagram to visualize these temporal relations. So in Hayes diagram, each node represents a year's network and an arrow is drawn only when one year's edges are fully contained in the other. And it is useful because it avoids clustering and it gives us like a minimal way to show how networks grows or shrinks over time. But most importantly, it is helpful in understanding the direction of change. So whether the price similarity increased or whether certain edges disappeared across years or not, we can tell that by Hayes diagram. Here is an example of it. In food, staples and grain category, we saw that in 2024, network contains all the edges from 2023, and this means that the city became more aligned in their price behavior. And then from 2024 to 2025, the overall structure stayed stable as well with only small changes. And this shows that how we can use Hayes diagram to make it easy to trace the evolution of the price similarity over multiple years. We then, in our next experiment, tested how changing the cosine similarity we tested like how changing the cosine similarity threshold affects the network. So lower threshold creates dense network where almost all the cities look similar, and as we increase our threshold, only the stronger relationships left. So for example, in when the threshold was 0.80, we saw a node was happening, but when we increased it to 0.90, we saw that we lose that node. In our experiment H4, we calculated 4 major centrality measures to understand each city's role in the network. So degree shows how many direct relationship a city has, while betweenness shows which city acts as a bridge. And eigenvector centrality highlights the influential city connected to other important cities by comparing multiple wing schemes. Here is a graphical representation of it. As you can see, based on different wing schemes, there are different results. Then our next experiment H5, we combined all the experiments, and as you can see in the graph, this is only for the utilities and transport cosine similarity map between all the cities, and from that graph, here are all the key insights that we got. Cities tend to cluster by product category, and utilities and transport show the strongest nationwide consistency. So we got that the utilities and transport is the one factor where we saw the most consistent results across all the country, right? So the temporal relations helped us see which year strengthened or weakened in similarity, and weighted centrality revealed which cities play the most influential role in shaping price behavior across the country. To conclude our project, it shows that similarity based network analysis is a powerful way to study pricing behavior across cities and across time. Cosine similarity, thresholding, and temporal relations and centrality together reveal how market evolve and which cities drive these changes. Overall, our approach provides a clear data-driven picture of price cohesion and regional alignment in Pakistan.